Okay, ready to go? Oh man, I was ready to go. Better. Jared is on Zoom. Cheater, Jared. It's so unfair. But nevertheless, it's better to have you here than not. But what is it I'm trying to do? Just here just a second. Okay, guys, so today it's time for us to discuss your potential projects, right? Because we only have like 1.5 months left. So we should probably talk about what is it you can do. So as I was mentioning the other day, right after the fall break, some people already figured out their potential project topics. But today I came up with a list over the weekend, which looks interesting to me. What I will do today, I will try to explain what this project means, because the way, unfortunately, the amount of time we have is kind of not really sufficient to let me I mean, first of all, yeah, you're very welcome to pick your own project. That's totally fine. Just talk to me. But the way, the amount of time we have, there is not enough time to kind of teach you the field and then tell you, okay, now it's time for you to pick whatever you want. So we are short of time, right? So because half of this semester we kind of talk about we would say third of the semester we talk about Linux, and once what's wrong with Linux, then we talk about virtualization. Now we kind of passed half of the semester, right? And we didn't really talk about what can be potential research challenges in that field. So today is the day. But so let me introduce a couple of those, and some of them kind of naturally follow from what we were discussing in class, and some of them are completely kind of potentially brand new to you. So it's something what I was thinking of looking at over the last couple of years, not actively, but potentially. Okay, so cool. So just a reminder, our end goal in this 1.5 months, which we have, whatever, the middle of December, right? To do something what is equivalent to a short paper. It's an ambitious goal in 1.5 months, but again, maybe it's doable. The reason why it's important is that if you manage to assemble a paper and put it in your resume, it increases your chances of getting a better job, better offer, or finding a research team you want to collaborate with, stuff like that. If you're a PhD student, obviously, you understand the benefits. If you're not, then the benefits are, the tangible benefit is better offer, because you will be you will look better on paper and you'll be smarter to begin with. It's also enjoyable to work on those things, right? And some of them are kind of cutting edge things, and some are less. But nevertheless, so, and you're welcome to team up, because some of those projects are too challenging for one person. But if you want to do it yourself, go for it as well. But yeah, you will have to try to talk to me as much as you can, trying to figure out the guidance. Okay, cool. So I don't know. I asked a couple of weeks ago about, do you guys think about potential projects which you want to work? Did anyone? Besides the people who started working on something? No ideas. No one has any. Okay, cool. So my very logical thing number one is to try to build a scalable buffer cache. So we spent some amount of time, remember, when we talked about Linux, we said, okay, each file will be represented by an address space, right? So a file is from some address 0 to some address max. And every time you do a read, a write, or a read call, you say, look, I will maintain some amount of this file data cached in memory, right? And you say, look, okay, cool. So there might be like multiple ways to do it. Remember in x6, who remembers buffer cache in x6?
Buffer cache is when you write to the file system.
Well, buffer cache is a cache, right? So you retain or cache some amount of these blocks.
Yeah, every time you read or write, you first write into a cache. The buffer cache.
Yeah, you try to find a hit in a cache.
Yeah.
But do you remember how x86 was implementing the cache? Anyone?
Linear search.
A linear search, good.
Yeah.
Linear search. What was the data structure used for the buffer cache?
Linked list.
Correct. Linked list. So they had an array, which represented the storage for the buffer cache, and then elements of the array were linked by kind of like next and previous. So it's doubly linked list, and they used the list LRU algorithm to promote the frequently used elements of the list. So if you access this one, you promote it to the beginning of the list, hoping that you will amortize the search over multiple times, right? Yeah. Okay, so a project, right? Scalable. So what was the scalability bottleneck of this buffer cache implementation? Who remembers? It's almost like an exam.
The tree, right?
The tree, the what? Scalability bottleneck of x86 buffer cache.
Was it shared by all the processes?
Correct. So there is a couple of design choices which were a little bit odd, right? First of all, the buffer cache was global for the entire system, not per file. Although you would imagine that, you know, you can probably maintain something per file. They maintained one global, like no matter, any process could read any file and place an entry in the buffer cache as a result of it, right? But what was non-scalable? Where is the scalability issue here?
The big log.
The big log around the search.
Yeah.
Correct. So agree, big log. So I'm glad that you remember. That's good. So everyone else is on board. So when you were accessing any operation on a buffer cache, required a big log over this array, right? There are multiple, like it's a bottleneck on multiple levels. Level number one, that no one can proceed over this giant data structure. So meaning that even if you make it larger, it's unlikely that performance of a highly loaded system will improve, because everyone else still will be waiting for that one process which came first, right? That's one. But second, we also remember that it was using non-scalable logs and it was competing for one cache line. So that's a second, I mean, because you have to first solve the problem that multiple processes can access the buffer cache. But second is like make sure that the locking primitives or synchronization primitives are scalable, right? Agree? Okay, do we remember how Linux was solving the buffer cache? What data structure they were using?
RBT.
It was a tree. I don't think it was it Radix tree. I think it was Radix. Which was representing, first of all, they made the choice that it's per file, which means if other processes don't even read this file, there is no conflict, right? However, there might be a conflict for allocating pages for placing into this, like into the buffer cache. But they had a tree, right? This Radix tree. And I mean, to be honest, you wrote this homework assignment, right? So I don't remember exactly how the synchronization was. I don't remember the granularity of locking on that tree. But if I remember correctly, they actually discarded it in the very recent versions of Linux. And they replaced it with a different tree. Which one? Who remembers? Range, something range search tree. What was that? But anyway, so they said, okay, look, this tree, if I remember correctly, this tree was not scalable enough. So granularity of locking was not good enough. So this project, I suggest the way to go about it. I mean, ambitious person can say, look, we're gonna implement it in Linux. It might be a little tough. I would say you can implement it in x86, replacing this buffer cache, but still run some tests on like multi-core, run on physical hardware, where you can test the like scalability of your data structure on the real hardware. Which data structure to put here, that's a question. So the way you go about any of those projects is that you first read what was done in the field. Maybe this is a solved problem. Maybe I mean, typically there is no like a finite definitive stop sign saying, okay, we're done. This problem is solved. You can always improve because the hardware is changing, the workloads are changing. But nevertheless, for any of those projects, step number one is to read. So, I mean, and step number 0 is, of course, to search what to read. So essentially, you go to Google Scholar and you search, okay, scalable buffer cache. Let me illustrate it for you. I haven't done it, so I don't know what the result will be, but essentially that's how you start. Scalable buffer cache. DRAM cache. That's probably reasonable, scalable for whatever reason. User. Unfortunately, this one is not cited, so that's a little dodgy. So, you know, like we usually want papers with citations. We maybe scalable page cache. But so don't have a good hit for you here, but nevertheless, so first search what to read, understand the problem, then read the papers, make some conclusions about what data structures to use here. And I mean, like, there's obviously, like, when you don't have enough experience, it's very easy to get intimidated and say, look, those people, they just published a paper last year at one of the top conferences. So they definitely know what they're doing, right? So that the problem is solved. Usually it's not the case. So people do different assumptions about what is solved, what is unsolved, right? And their goal is to publish, right? You can often improve. So that would be fun. So the reason I'm interested is that we're building those clean slate tiny microkernels, and we rarely can build a benchmark on a file system just because we don't have a good buffer cache, because no matter how hard we try, anything what we do hits in a like lack of a buffer cache thing, right? So we just cannot do anything fast, right? Okay, so that's any questions about this one? Another way to approach this problem is to, like, again, sorry, like you can read this, but you can also read the Linux / FreeBSD. I mean, the source code of existing buffer caches. Just again, understand what people are deploying in production today. And you can also measure scalability of those solutions and essentially say, okay, you would believe that this buffer cache is scalable. What are the scalability? Like if this was a Redis tree, which Linux was using, so what is the bottleneck here? Is it granularity of locking? Is it a single spin lock? I mean, it can be anything. I don't know what the answer is, right? But suggest you to spend some time on it. Questions about this one?
It's called Excel or something.
Say again?
Excel. So it's like kind of tree. So it uses some kinds of grids to go to like different layers. So one layer has
So
X.
access. I forgot. They replaced it, right? So Radix, lockless page case. Oh, this is better. So lockless. Which one what's the name? Which one is X what?
X. Yeah.
X. XA. Man, I cannot hear what you say. But why is that? But they recently like put a new. I thought that they put a new one, and it sounded different from what you're saying. Linux X-ray.
Yeah.
Maybe this one, yeah. So take a look. But anyway, would be fun to build, but you know, like as I said, don't get intimidated. Linux engineers may have their own choices, right? You can do different choice. I would there was a couple of different log-free tree designs. So one popular one was, I think, was called Silo or something like that, by people from Harvard, Eddie Kohler. So it's possible to like. It was also, I think, a Radix tree. No, it was B+ tree, I think. It doesn't matter, but you can experiment with those data structures and see what the scalability bottlenecks are. Okay, project number 2 again. So this, remember we talked, the reason for those projects is obviously that we talked some amount of time about scalability, right? And so when we spent like some amount of time, we looked at, for example, this paper. It's a paper by people from MIT, which says, okay, you know, like 10 years ago, so the way to remember is to just check the URL. It's OSDI is one of our top conferences. It's from 2010. And they essentially were studying the scalability bottlenecks in the Linux kernel. I forgot if I assigned this paper, probably not, probably did not, but because it's a little bit convoluted, so it's not, it's a little hard to learn something from, right? But what they say, they took like a representative set of benchmarks and ran them, and they essentially, while doing this, or at least this is the way how the paper is presented, maybe their process was slightly different, but in the end, they came up with different like scalability bottlenecks in the Linux kernel 10 years ago. Like we remember we specifically in my lectures, I was using the Exim example, like a bunch of those things. Exim, if I remember correctly, is a mail server which opens files a lot. And remember, we had this example on a mount table. It was a hash table lookup on a mount point, right? And that was a scalability bottleneck because you had to acquire a spin lock. So I think it's this one. So it's acquiring the directory entry, entry spin lock, right? And so they said, okay, use log-free protocol for checking file name matches, right? So they came up with a solution. They identified the problems by running real benchmarks, Apache, Exim, MFD, stuff like that. And they solved some of them. So they came up with this idea of sloppy counters. I think I explained them in this class, right? Like different techniques. Okay, good. 10 years ago, supposedly they solved it. The question, however, remains like, kind of, are we there yet? Yes, there is regularly some other papers, like for example, this one, NROS. So Ryan Stutzman is among the authors, collaboration with Ryan Stutzman is a professor here at the University of Utah. Other people are from VMware predominantly, right? They said, okay, look, scalability is still an unsolved problem. And they came up with this operating system architecture, which essentially, instead of like acquiring blocks to update the shared state shared between multiple cores, they use a explicit replication protocol. What it means is that, I mean, there's a variety of those. They use something what is called NR. Man, I forget what NR stands for. Now replication. But at a high level, it kind of like sends, it updates the copy on one core and then sends messages to all other cores to kind of reflect the update. And they said, okay, this is the way, this is the path forward, because instead of like coming up with a very funky localized data structure like a tree, we'll have a tree which is optimized for a single thread. However, we will propagate the updates on that tree to other cores, for example, right? It's controversial. They say, you know, if you look at their benchmarks, they say, look, by the way, we're beating performance of whatever. Like, for example, here, like LevelDB on an ROS runs a little better than like on Linux, right? Of course, the question is whether they are right or not, and maybe we want to answer this as we go about this project as well. However, the conceptual question which we want to answer is 15 years later, are we there yet? Or Linux still has scalability issues? And if it does, then which ones? It's a little hard. You have to work with real Linux system. The question is like how to even identify those bottlenecks. So probably you will have to learn how to use some profiling tools like iPerf. Perf. On Linux, it's called perf. Performance counters, right? It uses hardware performance counters to identify the bottlenecks. It's still completely non-trivial. Run various application benchmarks and identify those bottlenecks. And maybe Intel vTune, a slightly better profiler, it uses the same hardware performance counter, but however represents, it's kind of part of this human computer HCI discipline that you collect the same amount of data, but you represent them better, and it's easier to make a conclusion. Sometimes it also guides you better towards what is it you need to collect. Why this project is appealing? You know, in industry, you say, look, like you come to industry and they say, well, we're running something that's maybe fast, maybe slow. We don't even know. Because, okay, we pay money to Amazon, like some amount of millions per month, but we don't really know whether it's fast or not. And they pay you a fair amount of money to understand whether something is a bottleneck in their code, right? Or on their application workflow. So being able to use those tools and being able to make conclusions about, okay, something is a bottleneck. There is like a famous person, I forgot his name, but he used to be hired by all sorts of companies, maybe even Netflix at some point, but essentially his whole life is like using those tools and explaining the bottlenecks in systems, in system workloads, right? Greg, I think his Zapang, do you know the name? I always like, what's that? Who? Linux for I think I just want to figure out the name so you can probably this one. That's his blog post, I think. Yeah, Vernon Greg. Yeah. So this guy, he wrote it. And it's pretty amazing. That's him, right? So Brandon Greg, I would assume that he wrote that because he worked for, okay, this is maybe like rebranded as a like from Netflix team, but he was behind probably most of it. So there is fun. But however, as researchers would say, look, we don't want money today. We want it tomorrow. But today we want to understand what these bottlenecks are. And ideally, if we can address them, come up with techniques similar to how MIT people did it, address those bottlenecks in the Linux stack, right? I have one anecdotal example, which I will share if you pick this project, but it was a little surprising. There was a paper which claims like, let's say 2x performance improvement over something. At a high level, like they are sending messages between two cores, which is an interesting kind of like thing on its own. Like the question like how fast you can send data from one core to another. And like there's a range of papers in this subject because like it matters sometimes. And typically, so remember in this class, when we talked about Xen virtualization, for example, split device drivers, they maintain this ring buffer, they usually draw it as a ring, right? Remember the paper that was assigned like last week. And you typically update the pointer as it goes around the ring, right? However, physically, the ring is this, right? And every time you update, you say, look, by the way, I have to check whether I reach the end of this array. And if something, I have to wrap around, something along those lines. And those guys said, okay, this, in some extreme cases, this check takes you so much time that it affects your performance. Like simple if I remember correct, what they did instead, they mapped a page of memory here as, let's say, inaccessible. And only when the pointer was hitting this page, they were catching the page fault through a signal mechanism. And in their setup, this page fault was so infrequent that this technique was faster than checking on every axis. So essentially, you think of it, it's like an infinite array. You always access to the next element, but at some point you hit a page fault, which means that you reach the end of it, and you wrap around. And let's say page fault processing is like 10,000 cycles, but if your queue is, let's say, 10,000 elements, that means that it's one cycle per axis, right? So it's interesting. And we tried to implement this technique, and unfortunately, we didn't succeed. We did succeed, but there was a performance bottleneck on essentially when you handle this page fault in a single core, there's a lock in the kernel, and everything is fine. You get 10,000 cycles, let's say. Their paper is valid. We tried to scale up and implement those queues from like running between multiple cores. And this spin lock on the page fault handling pass became bottleneck for us because we were hitting this page fault from multiple cores. So it's, of course, it's a very aggressive kind of corner case, which probably will never like kind of discover on a real workload, but nevertheless surprising, right? Okay, any questions about this one? So yeah, go ahead.
How to measure the speed from one core to another core? How to measure this?
How to measure? So you just like run it in the loop, send like say 1 billion messages. Here you said RDTSC to read the timestamp counter, and then RDTSC again here, and you divide by the number of messages sent, and that's your throughput. And you know how many of those. And of course, you get blocked. So if the queue is full, then you just stay there. Right? I think, okay, let me tell you. I said that they were saying, okay, it doesn't matter. So it's anyway, it's okay. So anyway, scalability is an interesting problem still. There will be again a bunch of papers about it. So maybe I'm missing the point. Maybe people already wrote this paper, Linux scalability 15 years later. So again, the first step is to like search for those existing papers and see where the field is today. So maybe like, there's so much done that this is not even a problem, but then you just exit with a survey, say, okay, I understood what's going on in this field and I'm fine. Great. Okay, project number 3. So we kind of never really talked about this problem, but you guys remember what TLBs are?
Yeah, trade to classify buffer before going to work the big table.
Correct. So TLB is a cache, which caches virtual to physical translations, right? It's on the CPU, silicon, right? Yeah. So every time you want to access an address, in the same cycle, you do 2 things. You perform a TLB lookup and you perform an L1 cache lookup to understand whether you have this cache line cache, right? And TLB essentially caches virtual to physical. If you don't have a TLB hit, then the hardware says, okay, I know where the CR3 is pointing, and I'm going to walk the page table, figuring out the physical address. And after that, the input here is a virtual address, the output is a physical, and then if you like translation succeeds, there is no page fault or anything, the hardware pushes it into the TLB, right? The problem here is following, right? So it's a beautiful thing, obviously. That's why you can imagine walking the page table on every axis. So it's like some hundreds of cycles, right? I'm kind of playing that even if those are cast in like L1, L2, L3 hierarchy, the last leaf may be, if you have truly random access, the last level will be not cast just because you ran out of space in L3. So that will force you like 200 cycles to really read this entry from top, right? Because TLBs are beautiful. However, each CPU has its own TLB. They are not synchronized, right? So TLB on another CPU, well, imagine you're running two threads, thread 1 and thread 2 from the same process, because it's maybe Apache web server or whatever your database is, right? And they accessing the same virtual address, right? Maybe it's whatever, some shared data structure. You already acquired the spinlock. Maybe it's an address of a spinlock itself, right? So of course you will like on this CPU, which probably will have a pointer to the same, it will have its own physical CR3, right? I hope that you understand this. It also is going to walk the page table hierarchy and will insert this translation virtual to physical into its own TLB, right? Agree? Beautiful. And they both will run happily and fast. However, what happens if this page, which we're accessing, somehow gets reallocated? Just suddenly this data structure, we accessed it once, maybe it was an incoming request. We accessed it once and we said, okay, that's it. We no longer need it. So you say, in C, you say something like a free goes to like some kind of a whatever multi-level allocator, which implements efficient allocation of some objects. If it's a whole page, maybe you say something else, but eventually the allocator might say, okay, unmap, or like kind of like go back to the operating system, like in x86, it will be SBRK, negative numbers saying, okay, this page is no longer needed, right? What needs to happen to the entry in the TLB?
Flush.
TLB flush, right? Because if the operating system leaves this entry, it effectively allows the code to access the same virtual address again, right? You unmap, like TLB, the CPU doesn't know anything about it. So you have to really say flush. In the past, like when it wasn't like a performance problem, the whole TLB was dropped, but then you have to walk the page table over to repopulate the cache, right? Not a good idea. Now they can flush individual entries. So they will specifically flush for this virtual address, right? So this virtual address, of course, like on this core, you said unmap. Like you, with the syscall, you enter the operating system kernel, internal operating system kernel says flush this entry, right? Okay, problem solved. So this entry is removed from the TLB, right? What's the problem?
You need to search where is this entry.
Well, no, search is done by the hardware. TLB, you only have like a flush instruction which takes a virtual address for which to flush. Who knows the answer? Yeah, the other core, Jerry, we're glad to have you here. What about this entry? No one said flash for this entry, right? Which means that this other thread can still use this virtual address, right? That's a problem. Agree? How to solve it? What's the solution? How does Linux work?
There should be some kind of inter-process communication before flushing these.
Correct. They say, look, we really need to flush this entry on this core, or rather on all cores. There are different optimizations because broadcasting to all cores is a little too much. They say, look, we're going to track on which cores this process was running and flush only those cores because, you know, they track it. But still, how to even like, if it's just two cores, how to even like trigger a flush on another core? Who knows? what is inter-process communication? Because it's not inter-process, it's inter-processor, right? Because it's your operating system kernel, and you have to somehow trigger execution of a flash on this core. On the other core, how do you do this? We've seen it in x86. Although actually now I'm confused. I don't remember seeing the TLB. It's called TLB shoot down, this problem. How does x86 implement TLB shoot down? Do we know? I don't. How? People tell me. There is no code which does it in x86. That's a good question. I don't know the answer. In x86, not on top of my head. Although I think I do. Okay, got it. I know the answer. Do you guys know the answer? Man, I will fail everyone in a second. It took me 10 seconds to figure it out. So you should do it at least like a minute. So how does it work on x86? Maybe, but not good enough for my interview, if I may.
Switch from here to there.
Okay, why does it work in x86? Who knows the answer? Safan? Hiding. You should know the answer. Jerry? It's very easy. It's easier than I thought. Say again. Kind of. You're right, almost there. But can someone give me a good answer? It's a little surprising, but okay. Here's the hint. Not a hint. x86 doesn't support threads. Right, so this situation doesn't arise. In x86, it's 1 CR3 per process because there are no threads. At this point, you have a guarantee, an invariant, that you're only executing this process on this core. If you're doing this on map or SBRK, whatever, they will flash an entry on this core, and you have a guarantee that this process is not running on any other CPU, meaning that and every time you switch from one process to another, x86 actually flashes the entire TLB because they reload the CR3, and they don't support something what is called a tagged TLB. But for example, like in my class, x86 class, I don't have it every year, but occasionally there is a homework which says extend x86 with support for threads. And this is immediately it's very easy. You add threads, but without the TLB shutdown, you're introducing a huge bug in x86, this bug, unless you implement a TLB shutdown, right? Is it clear, my explanation for why it works? Yes or not? Clear? Okay, cool. So it works in x86, thanks God. But okay, Linux does have threads, right? So the question, so what does Linux do to make sure that they synchronize TLBs? How is this TLB shutdown is implemented? Anyone read about it ever?
Just kind of
good.
Just look it up. Just from what I'm reading right now, it's just by reloading CR2 and 3.
Yeah, reloading. Yeah, so this allows you, instead of using one flash of a specific cache line, you can reload CR3 and it flashes the entire TLB. So it's an answer, but modern operating systems, of course, don't do that because it's too expensive to lose the entire TLB cache. But how do they synchronize? How do they trigger a flash on another core where another thread potentially is running right at the same time? potentially even accessing the same virtual address. Okay, I mean, you probably don't have to know, so that's for real. So that's why I'm using this lecture as partly to explain this. What they do is that they send something what is called an inter-processor interrupt. We've seen it in x86 only once. When x86 boots, it sends an inter-processor interrupt to wake up other cores because they are sitting in some like boot state, like spinning, whatever, not even spinning, probably some hardware. I don't even know what they're doing, but essentially they are not running. And this inter-processor interrupt is the mechanism which allows you to say, on this core, I will trigger an interrupt on another core when this inter-processor interrupt is delivered. And then you process an interrupt inside the interrupt handler. Like again, in Linux, you go from interrupt handler to some kind of a higher level mechanism, like software IRQ. Probably I did not explain them in this class. Maybe we'll come back. And essentially it does the flag, right? And of course, you have to keep spinning here, waiting for this acknowledgement of this interprocessor interrupt, because you cannot return to the user saying, okay, we unmap this page, or even return this page back to the allocator because it's still mapped potentially on other cores, right? And obviously, these interprocessor interrupts are not cheap. So it's like some number of hundreds of cycles, plus some processing in software and some acknowledgement, right? And people were like working on optimizing those TLB shootdowns. So like there was a couple of historical papers like this, this multi-kernel, which is called Barrelfish. Like at some point, I mean, this team became like very kind of like, I mean, those people used to be famous, but it was at some point the sexiest systems project or operating system project that happened, I think, by 2009. So this Andrew Bauman, I know him, Simon Peter became a professor. Andrew is a high-up researcher. Timothy Roscoe is like, he was a professor, he's now a professor. So anyway, cool. So they said, okay, like we're gonna be building an operating system somewhat similar to this NROS. Again, so it's like kernels are replicas which synchronize with each other through messages, right? And so you essentially say, look, it's faster this way. Then again, if I go back to my second link, an ROS also with this replication, which I mentioned, right, from Ryan Stutzman and others, it also looks at TLB shutdown as a case study to optimize. But okay, if you're not convinced that this is a problem, so there is this guy, Nadav. He used to work for VMware. Now he's a researcher. He's a professor, so now he's a single author, but essentially he does it in Linux. He says, okay, you guys I love your exotic stuff, all your Barrelfish, multi-kernel, and ROS. You guys all suck because we really need to run like real systems, Linux style. And we need to optimize this business of sending those APIs. And he's not unique. So like he has multiple papers on the topic. So another one, like is this one, don't shoot down the TLB shutdowns. He's still at VMware, but he's a very good kernel hacker. And so, and a researcher as well. So that's essentially, he studies how it can be done on Linux, right? Okay, cool. So clearly it's a problem, and he's not alone. So there is a range of these problems, right? So what is this project about? The project is, the question is, why don't we have coherent TLBs in hardware? You know, we have cache coherence, right? Meaning that if I change the cache line on one core and someone tries to read it, or some other core tries to write it again, right? So we have a hardware implemented protocol which balances this cache line and synchronizes, right? So it's like concurrent readers, exclusive writers, right? Or whatever we call it, messy, right? Modified, exclusive, shared states, right? Right? Okay, so the question is, why don't hardware provides cache core coherent TLBs? Apparently, it will eliminate this problem altogether, right? There were attempts in the past to do this. So they're like, if you look up the literature, you will see that people were rooting, like hardware architects were rooting for core coherent TLBs, but they didn't took off. I don't exactly know why. So, and the question in this project is trying to figure it out. Essentially, unprohibitively expensive, meaning that right now the TLB lookup is under one cycle, and what it will be if it's cache coherent, maybe it's 2 cycles. Does it like, yeah, it probably changes everything as well. Instead of 1 cycle, it's 2 cycles, I don't know. Second is like, what if we build them and maybe we will tolerate this 2 cycle difference, like, or penalty. The question is like, on what workloads we're gonna gain significant performance gains, right? So those papers like an ROS and whatever the Nadav was doing, they essentially say, look, they were trying to justify their research, right? So they run benchmarks saying that, okay, yes, it's a problem. So, and your goal is to also understand on what workloads it's a problem, maybe do some kind of a CPU simulation to either in software or in hardware. In software, you can just say, okay, when we're gonna flush, instead of flushing, we never send an API, for example, but I don't know how to simulate the 2 cycle access. So maybe you will, like, you can do it, but we have to think about it, right? But an interesting, maybe it's time for the CPU designers to essentially provide this TLB coherence. If it's really a problem, I mean, it seems to be like a huge problem for modern systems, but somehow the hardware designers don't wanna work on it. So something stops them. So I don't know the answer. So we have to figure it out. Any questions about this one?
Say that your CPU that have
Or
what is the
no, it's all tag TLBs, right? So probably, I mean, I didn't explain the notion of a tag TLB, but typically in the past, TLB was 1 per core, meaning that when you switch from one processor to another, and you're switching the mappings, right? So because you switch the page table, you need to flush the entire TLB, right? Because otherwise the next process will be able to use an entry from a previous process, right? And access the memory of the old process, right? Okay, that's why when you reload CR3, you flush the entire TLB. But I keep saying you can actually flush 1 entry. Partially, it's just to implement on map, but second is that each entry in the TLB has something what is called a process identifier, or I forget how Intel calls it, but it's essentially an idea of a process. And so let's say it's 5. And the second entry has, like, let's say process number 3, which means that only the entries which match the currently running process can be accessed. If you have a hit, but it's from a different process, it's a miss, right? So because it's not yours. And this way, when you switch the CR3 from one to another, the TLB is not flushed, it stays. It's just that you only change the process identifier, right? From 5 to 3, you're switching from 5 to 3, right? And then 3 can, like, if 3 and 5 are the only two processes in the system, they keep sharing the TLB between each other, right? But you don't have to flush the entire thing, right? So I would assume that at this point, you don't have to track processes that much. It's just that if you track with this process identifier and somehow propagate it to other cores, you just have to invalidate this entry for this identifier on all cores. But how to do it, at the level of hardware, I don't know. Like, we have to come up with a protocol.
Make clear. So each CPU core has its own TLB.
Correct.
So if think about 2 cores, A and B, if one entry, the process in B wants to access is cached in A, the TLB of core A, but not in TLB of core B. So B has to go work through the page table.
It depends. So maybe if it's already cached, if it's a cache coherence like protocol, this entry can be just sent back, right? Similar to how with the cache coherence, like it probably will be somewhat similar to the cache coherence protocol, where like the entries are, let's say it was in the exclusive state, if you know that it only exists on this core, then maybe if you send it to someone, it changes to shared, and there is a directory somewhere, and at some point, if you say, look, validate this entry, it's a kind of a special operation state, can validate, make sure that you're unmapping it. So any core can issue an invalidate operation, right? Then it goes and like goes through the directory and it invalidates it on all the cores in hardware, right? Similar to how we
But
do.
you said team does not support this kind of hardware.
Right, modern CPUs, like, at least this like commodity CPUs don't, but in the past, I've seen papers from architecture community which were asking for this support. Maybe it wasn't an issue, enough of an issue back then, but the question is like, it seems that it is an issue now, but maybe it's so expensive to build that they don't build it.
So
But I-
without this hardware support, probably, but we could not share.
We do, the rating system just does this interprocessor IPI. They perform this TLB shoot down algorithm. This is how Linux works and every other operating system.
Also,
So it's done in software. This essentially, this coherence algorithm is essentially implemented in software. You flash on one core, instead of like hardware doing this very fast, you send an interprocessor
So-
interrupt.
so every time, when a thread or process in one CPU core try to access TLB, besides checking its own TLB, it will also has to try other cores TLB.
On modern CPUs, on existing commodity CPUs, the core will just walk the page table. But in this hardware implementation, if you believe that it's easier or it's faster to get this TLB line from another TLB than working the page table, you can get it from somewhere, right? It can be faster because if it's 200 cycles to fetch it, and it's maybe like 50 cycles to fetch it from a neighboring core because you're running on the same, like two logical
Socket.
threads, yes, same socket or like something along those lines. Right? I don't know, like, that's the answer. I mean, I don't know the answer.
Well, if there's about just like this as a classic thought. I think you know if they've implemented before, like tested like some sort of like TLB like orchestrator in the kernel space application to like manage TLB instead of like having, I don't know what like the performance order of that.
Well,
One of the
to some degree, the existing software solution does what you're asking for. It's just that maybe you want something, I mean,
More like, yeah, like.
What-
they
what-
kinda implement this next.
right, so like those papers by Nadav and others, which I didn't cite. They, in many cases, they want to avoid the interprocessor interrupt, and you can send software messages and say, okay, like I will set, like, will I update some variable, sending kind of a message in a cache line. On the other core, eventually message will get processed and they will invalidate the cache line, stuff like that. So different approaches were tried. I'm not an expert on this subject, but people tried, but the question is where we are today. So it's kind of interesting, I guess. So no answer, but the kind of the high level story here is that maybe it's time for coherent TLBs after all these years. So the question is, why not? I'm pretty sure that the architects looked at it, but I don't know why the answer is still no. So maybe we will change the public opinion. We say, look, the benefit is huge and such. Okay, next project is about building a very minimal hypervisor. So like historically, I mean, we just finished virtualization again. That's why partially the projects, I cannot come up with everything what I want to study. I have to come up with something what you guys can understand and put in context. And I only had so much time to explain things in this class, right? So you've seen Xen hypervisor. I was drawing it from the board a lot. You can imagine how KVM and QEMU works, right? And historically, you know, those companies like Amazon, Google, which implement serverless and stuff like that, for them, it's an isolation mechanism because if attackers suddenly escape virtualization boundary, they own the machine offline, and then can attack the data center as well, steal secrets, stuff like that. So historically, the size of the hypervisor becomes an issue, you know, because they are big. Like QEMU is big, this JIT compiler is huge, you know, who knows? Maybe it makes mistakes when like sees like a sequence of instructions, like, you know, jump, add, jump, or something like that. Who knows? You can pause them, right? And pausers will tell you, we'll find some bugs, but there will be others. And so people historically were trying to come up with a smaller and smaller hypervisor. And at this point, there's like a couple of existing quiet ones. There is a gvisor from Google. I think it's open source. Here's the link. You can look at the architecture. There is Firecracker from Amazon. Again, and there are multiple goals. It's both performance, but also security, right? And there is a couple I like. There's this nice hypervisor, which I use in my work because at some point I was trying to build my own, but like my students told me, okay, you're not going to make it on time. I really want, right? But they said, okay, first of all, it's not a contribution because who cares if you build another hypervisor, right? And second, like even starting, like the debugging remember this VMC virtual machine control structure. To get it right, like you forget some bit somewhere, like whatever, forgot to set some flag, it exits with some obscure error. Go figure out what you missed, and you have to get it right. So it takes some time. So I said, okay, I'm gonna quit, but there was this barrelfish. No, not barrelfish, Bearfly. Bearfly hypervisor, which is done by a security company, which is a government contractor. So, and again, it's reasonably very clean source code, stuff like that. So kind of minimal, designed to like build a hierarchy of hypervisors from very minimals to like to more to the ones with more features, right? And however, so Bearfly is nice, but it slightly had their goal was to sell it to companies who said, okay, we want security guarantees about isolation, right? I, however, want a slightly different set of guarantees in the long run. In the long run, I want a proof of correctness. So my team, so Japan, Gary, Donkus, not here, traveling somewhere, they essentially build those mathematical proofs now about the code. So they say, look, there's a mathematical, I can say model, but let's just say a specification which describes what the code is supposed to do, like let's send a network packet. And the actual implementation of the send method really sends. So meaning it corresponds or refines this specification, right? And in the long run, it would be nice to have a verified hypervisor as well, because then you have a mathematical proof saying, yeah, it really does what it's supposed to do, right? Before even doing the proof, it would be nice to have a starting point, like a small hypervisor, which we wrote as a test to say, look, this thing actually, this is what we need, it's just that we didn't prove anything about it, but at least that's what we want, because it's a little hard to immediately prove until you know what it's supposed to do. Like imagine like a sort algorithm, right? Your specification for the sort is easy, right? You say every next element is at least like either the same or growing, something like that. It's easy. But like specification for hypervisor is a little hard. So that's why I'm saying, like, let's try to build one. And you're free to use something like Rust if you like, if you like to experiment. Bearfly is written in C++, which is a little awkward because again, the more you come back to C++, the more and more awkward it looks. But it still has like some good, like very clean features. It's one of the cleanest code bases of which I have seen like recently, right? But it would be fun. And second goal here is that if you build a very small hypervisor, for example, which like as a toy runs x86 or maybe is implemented, we can build it in multiple ways. You can build it as a kind of a rootkit, which deprivileges Linux and like kind of sticks itself under Linux. This is what Bearfly is capable of doing. Or maybe it will be like part of the x86 code base. Then I will be able to teach virtualization more efficiently, right, in this class, because instead of like listening to me, I say, look, go read the source code, and here's an assignment against this source code, right? It's a lot of fun, but I cannot do it. I don't have it, right? So I can build it, but it takes time. So I choose not to, right? So it would be nice to build, but a long research goal is to like come up with a minimal hypervisor along the lines of this Firecracker, gvisor, maybe Bearfly, and then next generation, unlikely, I mean, I would say virtually impossible within the scope of this class, but come up with specifications and then build proofs. Surprisingly, it turns out that building proofs is not that hard it's much harder to write specifications than just building proofs. Okay, good. Any takers? Immediate takers?
Yeah, I guess, with the goal of like building the, because I was actually looking at the Python docs. And I guess you could have it as a goal to like kind of use GPython with it has a user interface.
Would love to build my own. I don't mind you to look at the source code of, for example, Berflang. I mean, the reason the way I arrived to Berflang is that there's like a famous minimal hypervisor, minimal rootkit from a security researcher, which rootkits Windows. So it's like literally a couple of pages of code. For me, it was too hard to understand because it's from Windows and I don't know anything about Windows. And second, it was very, very minimal. So it's kind of like sticks itself, but literally like a rootkit. So it can hide itself, but doesn't do much after that. So, and Berflang was slightly larger code base, and it also kind of had layers. It's like kind of like a toolkit, which allows you to build multiple, like kind of probably similar to JVisor, but I think Berflang was even first one. So I would prefer to look at Berflang first, but maybe JVisor is even better code base. I didn't look, so as a reference, like to understand what is it I'm building. I would prefer to build from scratch but we can talk about it. And again, you should understand that you don't have to like build. I mean, there is a critical core, as I said. Critical core might be just like a handful of pages of source code, which sticks a EPT page table and just like, when it gets an interrupt, reflects the interrupt into the guest, which is, again, on its own, a valuable teaching tool. If it runs, for example, x86 on top, I would be able to assign, and we can do some security research from that code base as well. But we'll see. Great, but
Actually, are we actually building a hypervisor? Meaning that we actually have or with Python or Firecracker, we can actually get that.
that's a good question as well. And I didn't want to go into the details, but if someone, right? So what, like JVisor and Firecracker, they also have a component which kind of like I think I forget which one, but let's assume Firecracker. It's just some kind of a LibOS version of Linux, I think, which interacts with the process, and this entire thing runs inside a VM, right? And then this is like, let's say, JVisor. And I looked at it some time ago, but the question is like, are we building this? Is that what you're asking?
No, like when you with Python or Firecracker,
So JVisor specifically reuses KVM. I would prefer to be KVM agnostic in this project just because it. Again? Both of them.
Yeah.
Got it. You're right. Okay. I'm just saying that JVisor conceptually says, okay, I'm still will be running on top of Linux using KVM for like managing VTX environments instead of like being QEMU, which usually was sitting like reacting to exits and stuff like that. They implement their own stack, right? Is that what they say? I would prefer to discuss it with whoever does it and maybe go clean slate with the goal that it's a little hard to reason about what's going on in KVM. Although there are projects like there is a team from Cornell which does verification with KVM, right? And supposedly has significant progress, although they verify only parts of it. And I mean, it's a good production choice, meaning that you obviously like backward compatible with whatever, with everything. I would prefer clean slate just for the sake of example. Although maybe it's impractical and maybe not even possible easily, but maybe it's doable. Not clear. Like I even want to understand myself what it takes to build one, right? So partially this project has kind of taken me far enough into this journey to understand. Like I've seen Berflang, I can kind of understand what it does, but maybe it's possible to do it in a simpler way, just to make sure that we can verify later. Berflang, the goal was to build clean code and run a ton of tests not even fuzzing, but lots of tests to kind of make a claim that, you know, like the harness is so good that, you know, you can almost convince yourself that it's correct, but it's still not correct, maybe. Okay, running out of time a little. Okay, good. But wanted to advertise a little bit. The practical value of this project is that, again, in the industry, whoever builds hypervisors is usually a very, I mean, you know, those teams will like you, obviously, because you have the understanding of what goes into this technology. So this position should pay in the long run, even if you're only starting today, but this is how we run our data centers. Everything is virtualized. And security and performance of the data center are critical, right? So if you have a, you know, if you're lucky and you use this project wisely, you can launch your career towards this line. Hopefully it will be successful. Man, I had so many ideas. Somehow I have to go a little faster. Okay, user level interrupts. So recently, let's say in 2021, in this new Intel CPU, which is called Sapphire Rapids, I think that was the first version. They implemented something what is called the user level interrupts. So typically interrupts are delivered through an interrupt table into a specific ring level. I don't know if it works well with ring 3, I should actually understand, but usually they send them to ring 0. But this user level interrupts allow one process running on one core to send an interrupt by passing the kernel. So the kernel is not involved altogether, just through the hardware. There's like a user level instruction, you enter something. I mean, both like the receiver, this is the receiver registers and hardware has some knowledge about something, but the moment if it's running on the core physically, operating system knows that it's running, obviously, then this interrupt is immediately delivered inside the other space of this process. And this way you can kind of like, instead of going through the kernel to like do an opcode here, you can immediately like reach the process running on another core, which allows you to again, we haven't yet talked about it, but typically in microkernel systems, like similar to how device drivers are running in a different VM in virtualized solutions. In microkernel systems, the device drivers are not running in a kernel because this kernel is so minimal that it doesn't have space and on purpose to reduce the TCP, for example, trusted computing based, the device drivers are pushed to user level. Again, it gives you higher guarantees of the fact that this user, if it finds a bug in this device driver, which is likely, then it maybe owns all this device process, but not own the entire system. Because if you find a bug here in a microkernel or in the kernel itself, then you own the entire system, right? And that was, I mean, I assigned a paper about security. I'll assign again one more today. We'll come back to security, but this is one possible solution, is to essentially run device drivers in isolation. However, without those user level interrupts, in order to reach this process, you have to send some kind of message through a microkernel into the device driver, or in case of Xen, remember they were establishing a region of shared memory where this read buffer was living, and maybe potentially you have to copy the request into the ring buffer or in some other region of memory and then just signal the other end. But it kind of gets slow, and with this user level interrupts, there is a potential to make it faster. So the question is to probably implement those user level interrupts maybe on top of x86 and measure their performance, and then maybe be able to make claims whether microkernel systems can benefit from those or not. And I don't know the answer, yes or no. I feel like, you know, I spend less amount of time on this project, right? Because it's somehow like I'm running out of time. Couldn't imagine it will happen. But it's equally kind of interesting because, again, maybe those device drivers will be running inside your, you know, maybe that's your gvisor, or the next version of gvisor, which your partner in this class builds and says, okay, this is my hypervisor, but where are the device drivers? They have to run somewhere. And you say, look, we will be using this user level interrupt to essentially allow like whatever Linux VM running here, send user level interrupt to this device driver VM to like essentially finish those missing bits of this virtualization architecture. I don't know exactly whether it will play out or not. Maybe it's still too expensive. Like some Intel engineers say it's a step forward, but they often make mistakes about like, you know, it looks faster than something, but you know, it doesn't really mean it. So it's still an open question. So I don't know the answer. Any questions about this one? Everyone wants to go. Good. Okay, think about it. Okay, what else do I have on the list? Man, 3 more. Let's go from the bottom. And the last 2 maybe we'll cover next time real quick. But you should, I will like, it's, the URL is there, so you can, I will add a little bit more links so you can start reading about related work or searching and deciding which is that which project. I will most likely ask you to commit to a project by the end of this week because we don't have that much time. Okay, this one is fun. C versus Rust. Everyone loves the Rust, right? Obviously. Everyone puts it on their resumes because you have to like write safe code. Safe means less bugs. There is this problem with Rust, that Rust is slightly slower than C, right? And let me just quickly maybe open up Linux. Okay, what is it called? Device drivers, Rust V versus C. No, let's do it. Comparison of what is it? So there was this paper. Maybe somehow I didn't have time to put a link, so maybe Columbia has a link here. No. Well, they have a lecture, which is nice, but no links. Essentially, there was a paper recently, which was a beauty paper for this class. I use it occasionally in some of my lectures, but they implemented a network device driver in 10 different languages. I was bringing it up. What is it? IXI, yeah. Avank knows what to search. IXI. I couldn't, somehow forgot the name. So this is the repo, and this is the paper. Resource paper. So they essentially said implemented the fast device driver in 10 different languages, right? Including Rust, but including even something like JavaScript or Camel, Haskell, Python. Of course, you say like Python definitely sucks. I mean, no need to like even ask me, but you know, Camel will probably suck even more than Python, right? So, okay, even like a little bit more zoom. So this black line is C. So it's clearly on top. Higher is better here, right? And this blue line is Rust, and Rust is catching up. So like originally there was a gap, but then it was catching up at the batch size packets of 32, right? This orange one is C#. So if you go work for Microsoft, you obviously will have to deal with C# maybe. Go work for something else, you will have to deal with Go, right? But they suck more than Rust, right? Definitely more. Never, like, don't even catch up here. So Java sucks big time, don't even try. Yellow line of Camel, surprisingly fast. Haskell is below. Swift, my gosh, something is wrong with Swift here. I don't know what. JavaScript, and then Python is obviously okay. Python just cannot do it at all. Okay, cool. So Rust is a clear winner compared to, but it still loses. Okay, so like here, there is a gap. This gap is roughly like here it's all like closer to 30%. With less than 30, right? Here it brings to something less than 20. Here it's relatively, right? Got it. Rust is fast, but not as fast. This is where, like, on your resume, it will play nicely. The project is asking you to figure out identify those reasons, essentially try to understand is it why and when ROS becomes slow. It's a little bit more confusing than it looks like. So Jafang and I and other people had a paper called Redleaf, OSDI. So in this paper, which we wrote, we asked the same question, but in a slightly more naive version. Essentially, we build a hash table, this plot. And we said, look, idiomatic Rust, this kind of like, so let's just look at it's one is normalized C performance. Idiomatic Rust is what Rust book will teach you to write, right? The code, which is like according to the good Rust style. Those two blue lines, they kind of always slower than 1, right? So sucking up to like 25 here, maybe even more than 30% on this data point, right? It's a hash table in Rust. However, if we write those red lines, if we write something what is called a C-like Rust, essentially, very, very much C-like manner, we just write Rust code. Sometimes it gets even faster than C. That's kind of like a just pure luck. If you look at the assembly code, it's almost the same, but like one loop has a check in front of the loop, another has just different compilers, generates the check at the bottom. Somehow it's fast, maybe it's like within the margin of randomness. So which means that you can write fast Rust code, but you have to try a little harder. And so this project tries to explore at what point Rust becomes, it's not like an inherent property of the language. It's more like a property of the code which you write. So for example, here we say if you insert an option type, it will be 1 extra, like, because it's not cast line aligned, it needs like a bit. If it needs a byte, then it's a full cast, not cast line, but you're less densely packed. So in terms of a hash table, it sucks more. But really, there are like lots of different corner cases which we don't even know. Like, the question is try to explore when and why Rust becomes slower. And of course, try to answer the question, like, is it possible to make it fast by either writing more careful Rust in a C-like style, in some other style, or maybe you can even suggest changes to the CPUs, maybe because, CPUs arguably were optimized to run spec. Spec is coming from C, right? So it's a code which is slightly different from code which is generated by higher level languages, which have like higher abstractions. Like maybe you have a vector, you do some additional checks on every axis, right? And in my C-like Rust, I just said, okay, I'm not going to use a vector, it will be an array. The check is so fast that it doesn't even matter. But maybe if you're a hardware designer, and we did those measurements and those papers, the ICSI paper also did those measurements, like how many more instructions Rust generates. Sometimes it generates almost twice as many instructions, and it's still as fast as C code. Why? Because the pipelines are so powerful, because there is such a huge, they're designed, they said, okay, let's put like, what is it, execution engines, right? So when you fetch from a pipeline, you say, look, you send to the execution unit, and you usually have more than you use in every given cycle. So if you have more instructions to execute, you don't even notice because the execution units execute them in parallel, right? And out of order. So the question is like, try to approach this problem and figure out when and why Rust becomes slower and whether we can address. Because obviously everyone wants the safety of Rust, because it means less bugs, right? Okay, I'll stop here, 3 minutes over. We'll come back to the other two projects, but I ask you to start thinking aggressively about what is that you're gonna do for your class project in this class. These two I will cover next time. Any questions? All good? Okay, see you then, what is it today? Monday. Okay, see you Wednesday then.